Welcome to example number 6. We have a model rocket that is attached to the end of a long rigid rod, and the rod is able to rotate around this frictionless pivot point, and it starts to accelerate tangentially at 1 meter per second squared for 10 seconds, starting from rest when it runs out of fuel at 10 seconds. So we're asked to find the total acceleration at 2 seconds and what will be the angular velocity in RPM when it runs out of fuel. To help visualize this, I found a neat little video from Pedagogy in Action, so let's take a look at this video. It's not exactly the same thing, but we have a disc that's being accelerated by the rocket motors here and here. So let's watch the video. So hopefully you noticed in the video that there was one point at which the fuel ran out of the rocket, and that in this problem occurs at 10 seconds. So let's write down all the given information that we know here. We are told that the rod is 2 meters long. So really what they're telling you here is the radius is 2 meters. So that's the distance from the center to where the rocket is and where it's accelerating. We're also told that the tangential acceleration that is due to the fuel of the rocket is 1 meter per second squared. And we know that it's going to run out of fuel at a time of 10 seconds. So that's when it runs out of fuel. However, in part A, we're asking for the total acceleration, we'll call that T1, at 2 seconds. So we want to know what the total acceleration is at some point while it's accelerating, but it hasn't run out of fuel at that point. So there's so many things that we can ask in this question, but let's deal with what the problem's asking here. In part A, we're asked to find the total acceleration. Now, if you recall, as something moves in a circle, if it's moving at a constant speed, then really there's only one acceleration, and that's that center-seeking acceleration called the centripetal acceleration, which is really due to a change in direction, not due to a change in speed because it's not speeding up or slowing down. So that center-seeking or centripetal acceleration is one acceleration, and we would only have that acceleration if it was moving at constant speed. However, this model rocket is actually accelerating tangentially as well. So there really are two accelerations, a tangential acceleration and a centripetal acceleration. So the total acceleration is really the resultant of those two. So you have a centripetal acceleration or radial acceleration and a tangential acceleration. So really, it's really equal to, if you think of this in terms of Pythagorean theorem, there's a resultant acceleration in that direction. So it's going to be the tangential squared plus the centripetal or radial acceleration squared. And it's going to be the square root of both of those. Now, we already know the tangential. We already know that is 1 in here. But we do not know the centripetal acceleration. So we have to find that out. So how are we going to find that out? Well, the first thing I can remember is the centripetal acceleration is the velocity squared divided by the radius. And we do know the radius, which is 2 meters, but we do not know how fast it's going. So maybe we think, okay, well, we do know that the velocity is related to the angular speed. Velocity equals r times omega. Will that be helpful? I don't know. Well, let's see. We don't know the angular velocity, right? Could we figure out the angular velocity? We do know the radius is 2 meters. How can we find the angular velocity? Well, we know that it starts off at rest. It says here at rest. So the initial angular velocity is 0. And we know that it's accelerating tangentially at 1 meter per second squared. And there must be some relationship between the tangential acceleration and the radial acceleration. Remember, the tangential acceleration is like that linear form of the radial acceleration. So the tangential acceleration is really the radius multiplied by the angular acceleration. So, and we do know that, and we know that. So we could figure out the angular acceleration with the tangential acceleration divided by the radius. So that would be 1 meter per second squared divided by the radius, which is 2 meters. That means that this thing is rotating at an angular acceleration of 0.5 rads per second squared. That's helpful because now we know how much it's accelerating radially. We know that it started off at 0, and we're looking at a time of 2 seconds. Hopefully you're remembering your rotational kinematics equations. So omega equals omega naught plus alpha times t. So the initial angular velocity is 0. We know that it's accelerating at 0.5 rads per second squared. And we're going to look at the point in time when it's 2 seconds. So the angular velocity at that particular point in time is going to be 1 rad per second. So now we know the angular velocity at 2 seconds, and we know the radius is 2, so then we could find the linear velocity, or the tangential velocity as we call it. So that's going to be the radius, which is 2 meters, multiplied by the angular velocity, which is 1 rad per second at that particular point in time. And that means that the rocket at 2 seconds is moving at 2 meters per second. So now we're ready. We can plug that into here and figure out the centripetal acceleration. Centripetal acceleration would be that velocity, 2 meters per second, quantity squared divided by the radius, which is 2 meters. So that gives us a radial or a centripetal acceleration of 2 meters per second squared. So we know our centripetal acceleration, we know our tangential acceleration, so now we can find the total acceleration. So we're going to substitute in. We have 1 meter per second squared for the tangential acceleration, and we just found the radial acceleration or centripetal acceleration of 2 meters per second squared. That gives you an answer of root 5 meters per second squared, or approximately 2.2 meters per second squared. Okay, so then part B is asking for what would be the angular velocity when it runs out of fuel. Remember over here, we can figure out the angular velocity at any particular point in time while it's accelerating. So we just really need to go, well, what would it be at 10 seconds? Because that's when it runs out of fuel. It runs out of fuel at 10 seconds here. So really just using omega naught plus alpha times t. So that's 0. That was the initial angular velocity plus the angular acceleration of 0.5 rads per second squared multiplied by 10 seconds. So we have an angular velocity of 5 rads per second. However, we want the answer in revolutions per minute. Let me rewrite that as a fraction. I'll just make it more like a horizontal fraction here. So then we can see that we're going to change this rads to revolutions and seconds to minutes. So in 1 revolution, we have 2 pi radians. So the rads will cancel out. And then we've got revolutions on top. But we got to get rid of seconds, so we have minutes. And 1 minute on the bottom, we want to have 60 seconds. So the seconds on the top will cancel with the seconds on the bottom. So they'll really have 5 times 60 divided by 2 pi. And that gives you 48 revolutions per minute, or sometimes people abbreviate this as RPM. And that's it for this example.